So we're going to change topics a little bit now and talk a little bit about some new methods that we're going to learn how computation works on these. And this is sort of an old technique. In fact, probably one of the decompositions that you're familiar with before entering this class are eigenvector, eigenvalue decompositions. So let's call these generically eigen decompositions. So these eigen decompositions are really powerful. And in fact, they are one of the ways that we learned that if you could take this matrix and do a decomposition, you get a lot of benefit from the decomposition itself because it has a certain kind of structure and a certain kind of form. And so I want to talk about this generically today as what do eigen decompositions do? And then what we're going to do in the next following lectures on this is talk about how do we actually compute eigen decompositions of a given vector or a matrix A, excuse me, okay? So remember, this is just a decomposition strategy. We're always normally just thinking about, I have some matrix in here. We're going to consider square matrices, m by m's, could be complex numbers. So that's going to be our matrix A. And then what I want to do with this is decompose this. I'm going to make relationship. I'm going to show how it relates to solving AX equal to B within this decomposition, but also some very interesting properties of A itself that the decomposition reveals. So I want to first start talking about what is an eigenvalue and an eigenvector. So what we know is if I take a matrix A and I multiply some vector x by it, what does it do to the vector x? When I talked about the singular value decomposition, we talked about all that a matrix multiply does is it takes a vector and it rotates it and stretches it. Okay? That's exactly what matrix multiplication does. Rotation and stretching. There is a certain set of x, however, where you could multiply this, and what you get back is the same vector stretched or compressed by lambda. So these are very special vectors. In other words, when I hit it with the matrix A, it doesn't rotate it. It just simply stretches or compresses the vector by lambda. Okay? These special vectors are called eigenvectors. And the lambda, in other words, the stretching or compression that happens, it's stretched if lambda is bigger than 1. It's compressed if lambda is less than 1. These are your eigenvalues. Okay? Eigenvalues, eigenvectors associated with a matrix A. And these are very powerful things if we can find them. Okay? Now, what I want to start talking about is how to find these and generically, and also talk about what these lambdas represent. I'm going to call, this is capital lambda. I'm going to call this as the collection of all of the eigenvalues. Okay, so this is the set of all the eigenvalues, lambda j, and this is called the spectrum. So the spectrum of a matrix. So another ways to think about this is normally when you think about a matrix, it's just a collection of numbers. Another way to characterize a matrix is through its spectrum, which is the collection of eigenvalues that describe that matrix. Okay, and this is a very common way to start thinking about what are called operators. This is a linear operator acting on some vector to do something, and this linear operator, A, has a spectrum associated with it. And oftentimes those eigenvalues and eigenvectors have some kind of physical meaning. And so that's related to some problem that you're trying to solve. So these are important pieces that we want to start thinking about when we start building out solution methods and ideas around eigenvalues and eigenvectors. Okay, so what I've shown you here is one vector to an eigenvalue, but really, generically, you may have quite a few eigenvalues and eigenvectors. In fact, up to, if this is an m by m matrix, you could have up to m different eigenvalues and m different eigenvectors. So let's represent these with a j here. So for instance, j goes from 1 to 2 all the way to m, because that's the size of this matrix. So I have a bunch of vectors, special directions, in other words, that when I take that special direction and I multiply by the matrix A, I stay in that direction. One way to think about it, each one of these x of j is what's called an invariant subspace. In other words, if I'm in that subspace and I hit by A, I stay in that subspace that's spanned by that x of j. Okay, so this is an interesting solution, and I could have m of these different ones with different lambda values for each of these different directions. One way to represent all of these solutions is to say, well, let's basically write them all together, and then you can write it like this. A, here's the X matrix, and let me show you what the A is. So A itself is the columns of the matrix A. X are your eigenvectors. So in other words, these are all the eigenvectors put into columns is equal to, again, here's your eigenvectors. Now times this lambda matrix, which is lambda 1, lambda 2, all the way to lambda n, the diagonal matrix with lambdas down the diagonal. So this is a representation of all the eigenvectors, all the eigenvalues together in one fell swoop. Here it is. Okay, so I'm very interested in this object here because it's telling me these x are the collection of eigenvectors. The lambda gives me all the eigenvalues. In other words, this contains the spectrum of this matrix multiplication. A gives me the spectrum. The spectrum is a representation in terms of these eigenvalues, lambda 1 through lambda of m. Okay, so that's an important way to start thinking about this decomposition. In fact, I want to now think about this. So hopefully everybody's fine with this. This is just writing out each one of these equations from j goes from 1 to m, and then in a compact form, here's all of those m equations written down in one way, in nice matrix form. Okay? So this is going to get us to an important point here, and this is why you've probably seen eigenvalues and eigenvectors before. Because now, once you have this, notice what you've got here. If I multiply by the inverse of x on both sides, then I have A is equal to this decomposition here. So the matrix A, I can rewrite as x times this lambda matrix, which is essentially the spectrum, x minus 1. So that's the decomposition of A in this eigen decomposition coordinate system in terms of its eigenvectors and eigenvalues. Okay, so this is an important result out of this. By the way, this is not guaranteed to happen for any matrix A. The matrix A itself has to have certain properties in order for you to be guaranteed an eigen decomposition. By the way, I want to really quickly contrast this with the SVD. I've made this point before when we were talking about SVD because it's really important to see how do SVD and eigen decompositions relate to each other. Notice in this decomposition here, AX equals X lambda, you are using the same basis x on both sides. So a single basis to do your decomposition. And then that decomposition, you have x inverse to get you to take this A into this decomposed form. We're going to talk about what that means more in a second in terms of diagonalization of a problem. But that's what you have, single basis set. Now, what I want to contrast to is what did we do in the SVD? In the SVD, we actually had a transformation, which was A acting on V was equal to UC, which gave us the decomposition A is equal to UCB star. Notice the difference between these. When we do an eigen decomposition, single basis, and I better have an inverse to this, and if I don't have an inverse to this, there's no way I can do this operation. Whereas when you have the SVD, notice the difference. I have the basis V and the basis U. SVD allows me to work with two unitary matrices, which are bases, the V and the U. By using two bases, I get this here, which this is just a unitary transformation. So this here, the star is just complex conjugate transpose. It's easy to compute. And we were guaranteed that every matrix had an SVD decomposition, irrespective of anything about that matrix. Always, always, always. And why is that the case? Because when you do SVD, you have a lot more flexibility because you have dual bases to work with. Whereas when you do an eigen decomposition, you're working in a single basis. And for these eigenvectors, you have to have, when you compute this eigenvector matrix, you have to be able to invert it, right? And we know that there's certain things. First of all, x has to be non-singular for you to have an inversion of this type. Okay, so that's an important distinction, but notice also the commonality. The commonality is that this decomposes it into a product of three matrices, with the middle one being a diagonal. This also does a decomposition to three matrices, with the middle one being a diagonal. So they have something in common, but one uses two bases, one uses a single basis. Okay, so that's an important distinction between the two. And most likely you've actually played around with this, and I want to show you one of the key features of this ability to do diagonalization. And it's always related to just solving Ax equal to B. So let's go ahead and take this, solve Ax equal to B in between these two methods. Okay. So let's solve Ax equal to B. And what we've been learning is all these methods to solve Ax equal to B, right? We've done QR factorization, SVD, we've done LU decomposition, Gaussian elimination. Now let's talk about it from the point of view of solving this Ax equal to B in terms of eigenfunctions, eigenvectors, eigenvalues. Now what we've said is the matrix A, if it has an eigenvector decomposition, that's the form it takes. Okay, so let's go ahead and say, if this is my decomposition of matrix A, if I can perform this decomposition, let's put it back in here. So I'm going to be able to put A in here to have X. Okay, I'm going to multiply on the left by X inverse. So X inverse X will be identity, and then I'll end up with X inverse over here. So you have you can now define this to be X tilde, this to be B tilde, and then your problem that you're solving is it's an Ax equal to B problem right there in these new variables. Now, what's the advantage to solving this into new variables? Check it out. This is a diagonal matrix. So this is trivial to solve because on the diagonal, in other words, the spectrum sits down that diagonal. And in this new coordinate system, you don't even have to do forward or back substitution. You can go row by row and just divide by the eigenvalue to get the value of x. And once you have those values of x in this coordinate system, you can come back out through this transformation here. That's the power of diagonalization. And that's why it became so important in physics and physics types problems, because what it allowed you to do is essentially move into a coordinate system where everything was diagonal. That's why it's so important in physics, is that this allowed you to go into a coordinate system where everything decoupled. Everything's decoupled here because everything's along the diagonal. In other words, every single component of that vector is independent of every other component. This is a really powerful framing of this problem in terms of a diagonal coordinate system. So diagonalization is just really a critical idea. And this is why so many of these techniques like SVD, like this eigenvector decomposition, are so commonly used because it puts you in a coordinate system where it's very natural now for you to write down solutions. Okay? By the way, before we move away from here, let me just compare this to what we did with the SVD. I just want to make sure that, again, I highlighted these when I covered the SVD. I want to highlight them again here so you really understand how closely related the concept of an SVD and eigenvectors are, but how in some sense more broadly applicable the SVD is. So when we did this here with an SVD, we said, okay, well, A is this here. So if you were to solve the same problem now with the SVD, you'd get U sigma B star X is equal to B. And then if I take the inverse of U, which is, it's a unitary matrix, so just multiply on the left by U star U is identity. This becomes sigma B star X equals U star B. I can call this X tilde, this B tilde, and then you have sigma X tilde is equal to B tilde. Notice how similar these are. This is exactly just like here. I've got a diagonal matrix times X tilde is equal to B tilde. So here I can just solve for each component of X tilde in this diagonal framework because it's independent of all other components. Both of these will take me order M operations to solve. When you do forward or back substitution, it's order M squared. When you do the full Gaussian elimination, or LU becomes order M cubed. This, once you get in diagonal form, order M to get to your solution. So this is the power of that diagonalization. If you can provide that diagonalization, everything reduces here down to a very fast order M solve. And then if you want to go back to your original coordinate system, you can just do it through whatever the transformation you had here. So you see the similarities. They're both exploiting diagonalization to solve AX equal to B. So that's a really important concept that we use over and over and over again. And this is why eigenvectors show up everywhere. That's more commonly what we think about, because a lot of the problems out of physics are what are called Sturm-Liouville problems. And in fact, we get this eigenvector decomposition to work. It's guaranteed to work because they're oftentimes self-adjoint problems where this is guaranteed to happen. So we just do this one here, where now we're learning that this SVD exists, and this SVD can do any matrix. This is always guaranteed to happen. There's no conditions on A. This is like, you can always do this. Okay? All right. So the question is, how do we go about solving for the eigenvalues and eigenvectors? So let's talk about that next. So we're going to talk about it from the point of view of theory. And then what we're going to talk about in subsequent lectures is from the point of view of computation. How do you actually do it with some kind of computational engine? Okay. So I want to solve this ax equal to b. And so in order to do that, I have to produce its decomposition. I have to get its eigenvectors and eigenvalues. So let's go ahead and think about this eigenvalue problem. Here it is. And what I'm going to do here is move the lambda x to the left side, ax minus lambda x. If I want to put these two together, this lambda is really down the diagonal. So what I would do here is rewrite this as a minus lambda I x equals to 0. Okay? So this is the manipulation of this to here. Now, how do we get then the eigenvalues? Well, we're going to do something that we usually try to avoid. What we normally think about is, can I invert this matrix? If the determinant is not 0, in other words, if it's non-singular, I can invert it. So if the determinant of a minus lambda I is not 0, then I can invert this matrix. Then the solution is x is equal to a minus lambda I inverse times 0. So x is equal to 0. So as long as this thing has an inverse, my only solution is 0. In other words, of course 0 is the solution. Put in 0 equals, what I'm looking for is an x that's not 0, a non-trivial solution. Okay? And that can't occur if the determinant of this is non-singular. What are the other options? Well, the only other option is, what if the determinant of this is exactly 0? In other words, it's exactly what we usually try to avoid, which is I'm working now with a singular matrix. In other words, the determinant is 0. And usually we try to avoid those problems, but here I'm going to try to make it 0. How am I going to do that? By picking the lambda values. I'm going to pick the lambda so that the determinant of this is 0. And if the determinant of this is 0, then it doesn't have an inverse. And then there's two options for x. Either I have a solution for this or I have no solution for this. And we're going to talk about these as we go forward with this. But I can find, in fact, an x that's non-zero that satisfies this equation. Okay? So what I want now is the determinant of a minus lambda I equals to 0. Pick the lambda so that that's true. And in fact, when you compute the determinant of this, we have our formulas for computing determinants of matrices. So if you do it on here, what you end up with is some polynomial, let's call it P of A, lambda, which is equal to the determinant of this. And what I'm looking for is the roots of the polynomial such that they're 0. In fact, lambda is an eigenvalue of A if and only if that polynomial is 0. Okay, so if you find a lambda value that's a 0 for this polynomial, you've got yourself an eigenvalue. That's exactly how we find the eigenvalues. Most likely you've actually dealt with these in the context of 2x2 systems. Oftentimes people have played around with doing 2x2 systems. And then when you do the determinant equals 0, you end up with a quadratic equation. And the roots of the quadratic equation are the eigenvalues of the matrix. And then we use those to say quite a bit usually about the kind of solution that we have and we're looking for. Okay, so it comes down to polynomials, looking for roots of polynomials. So that's the way we find the eigenvalues and eigenvectors, is making the determinant of this matrix 0, which results in a polynomial. And usually the degree of the polynomial, if this is an m by m, the degree of the polynomial is an mth degree polynomial. You have to find the roots for that mth degree polynomial. Okay? All right, so let me write some more on this. So here you go. Let me just generically write it like this. So that's my polynomial. I can break it up like this, and I'm looking for when this is 0. So your roots would be lambda 1, lambda 2, lambda 3, all the way to lambda m. So those would be my eigenvalues, or the spectrum of the matrix A. Okay? If each lambda j is unique, then they are simple. So that means, so each, in other words, if I find a lambda m of these, lambda 1 through lambda m, and each one is different, then each one of those eigenvalues is called a simple eigenvalue. Okay, and has what's called algebraic multiplicity 1. Okay, it's called algebraic multiplicity 1. So this is an important concept, because in fact, there are cases when you can have, and in fact, if you've solved, right, polynomial equations, or if you have polynomials like this, you can get what are called double roots, triple roots, right? This is where, for instance, lambda 1 and lambda 2 are the same. So this here would be lambda minus lambda 1 squared. So it's not a simple root, it's a double root. You could have triple root. In fact, you could have an mth root. Okay? And that, whatever, if you have an eigenvalue that shows up multiple times, the same, and it shows up k times, then it has algebraic multiplicity k. Right? And these are really interesting structures when you have multiplicities bigger than 1. You know, a lot of times, a lot of these eigenvalue problems, yes, it is the case that oftentimes you get algebraic multiplicity 1. There's a lot of times when you have multiple roots, double roots, triple roots. And in that case, some very interesting things can happen in terms of the spectrum, and then also in terms of the behavior of the system. Okay? And so part of what we want to do is consider what happens in these cases, or how do we start thinking about it. I'm going to give you 2 little simple examples in which you have these multiplicity ideas come and play a role. All right. So, but generically, if you have a root like this, if A has m distinct eigenvalues, that means all of them are simple eigenvalues. Okay, we'll come back to that idea in a minute. But this is it. So you're coming down now to root solving, and that's the way you set up these eigenvalue problems. You're going to do a root solving problem, which is basically something like this. Okay, and solving roots for polynomials actually can get fairly complex in itself. And we don't really care if the roots are imaginary. They will also have a meaning in terms of your understanding of oftentimes what the problem came from. So oftentimes when we plot eigenvalues in its spectrum, we look at the real part of the eigenvalue against the imaginary part of the eigenvalue. And so you might have a number of eigenvalues. Here they are. So it could have a real and imaginary part. What does an imaginary part mean? And a real part, it's oftentimes context dependent. but this can live anywhere in the complex plane. Okay, so there's no restriction on it living in real space. In general, they're complex. Okay. One more concept before we do a couple of simple examples. And this is the concept of you can use eigenvector matrices to produce what's called a similarity transformation. What is a similarity transformation? Let's consider for the matrix A, if I have my eigenvectors all arranged in X, which is some complex matrix, which is M by M. And since I could do this, this is a non-singular matrix. Okay. Then a similarity transformation, the transformation that takes A and maps it to X inverse AX. So what it is you take A, on the left, you're multiplying by the inverse of the eigenvectors, and on the right by the eigenvectors themselves. So this is called a similarity transformation. Okay. The nice thing about a similarity transformation is that this here, this object here, let's call this here B, is a new object B, then B and A have the same polynomial, characteristic polynomials. In other words, the P of A lambda is equal to the P of B lambda. Okay. They also have the same eigenvalues. And algebraic and geometric multiplicities. Okay, I'll talk about what geometric multiplicity is in a minute. That corresponds to an eigenvalue having multiple directions for the, and so having, in other words, here, algebraic multiplicity, it has to do with double roots. And then the question is, how many, for those double roots or triple roots or quadruple roots, how many different independent directions are associated with them? That's called the geometric multiplicity. I'm going to give you an example of that in a minute. So this is a really important property because oftentimes when we have some system that we're trying to solve with some matrix A, sometimes there's great advantage to work in these similarity variables, because now when you're in this coordinate system, oftentimes some nice reductions can happen for you. In particular, this is often used in reduced order modeling, where oftentimes what you do is you project into some lower rank subspace by doing such a similarity transformation. We won't talk about it so much, except for that you can use this to build yourself a new coordinate system. Okay? And a lot of these solution techniques, notice, they're just really about transforming yourself into a new coordinate system where you can take advantage of some properties in that new coordinate system. So when we did the eigenvalue decomposition, when I showed you AX equal to B or SVD and solved AX equal to B, notice what we did. Fundamentally, we moved to a new coordinate system where things were diagonal. And that's really easy to solve, right? So you transform into a great coordinate system, solve it there, and then you can bring yourself back. That's all this similarity transformation is trying to do as well. Take advantage of the properties of these nice properties that eigenvectors have, put yourself in a similar coordinate system, and then solve your problem there. Let me give you just a couple examples here of simple matrices, 3 by 3s, where we can start talking about these algebraic and geometric multiplicities. Okay. And what we're, like I said, what we're going to spend time talking about is how do we actually go about solving these things, because we want to solve these computationally. And what we'd like to do is, you know, we're going to have to solve for double roots, triple roots, quadruple roots. We want to be able to accurately produce the spectrum and all the multiplicities of the spectrum computationally. So when we develop our methodologies, that's one thing we have to keep in mind, is that we're after all of this from a computational point of view. So it's one thing to write these theories down or write down how you do it. It's a whole nother thing to come about it and try to do the computation itself. All right, let me give you an example of a matrix. It's super trivial, but there it is. Matrix A with 2's on the diagonal. It's a 3x3 system. If you were to take the determinant of this to solve for the eigenvalues, because that's what we found, right? We want the determinant of the matrix A minus lambda I to be 0. What you would end up with is the following characteristic polynomials. Lambda minus 2 cubed equals to 0. That would be my P of A lambda equation. Better. There it is. It's really easy to do, to take that determinant of not just A, but A minus lambda I. And that's what it is. So notice what you have here. When is this 0? When lambda is 2. So lambda equals 2 is your part of your spectrum. But notice it's a triple root, right? Because that's to the third power. So this has algebraic multiplicity 3. Okay? And here's what's interesting about this problem. You could say, okay, so I have these 3 eigenvalues that are all sitting at lambda equals 2. So one way to plot this is, here's your real of lambda, imaginary of lambda. And over here at 2, you have a triple root. Okay? And then the question is, what about the eigenvectors? How many eigenvectors does that triple root have? Well, it turns out you can plug 2 back into this problem here. Remember, you're solving AX is lambda x. Put in 2. Here's your A. Find the values of x that satisfy that equation. And in fact, you can get 3 linearly independent vectors. Here they are, 3 examples of E1, E2, E3. In other words, 1, 0, 0 is a solution, 0, 1, 0 could be a solution, and 0, 0, 1. So these are all eigenvectors. In other words, it has a degeneracy there, 3 eigenvalues, but each eigenvalue has a different direction. Okay? So the geometric multiplicity is 1. Every direction, in some sense, is independent of the others. So even though you have a triple root, which is the algebraic multiplicity is 3, the geometric multiplicity is 1. Okay? Sorry, geometric multiplicity is 3. Sorry, you have the same number of, so for each one of these, you get one of these. So this has geometric multiplicity 3 to go along with algebraic multiplicity 3. Sorry about that, I said that wrong. Okay? So this is a nice case in some sense because the triple root still gives you each eigenvalue, each multiplicity gives you a distinct eigenvector direction to go in. And those are the 3 that you could do. Okay? All right, so let's do a second example. And I'm not going to change it that much. All I'm going to do, put 1s right there. So it's a slightly different matrix. I put ones on this upper diagonal. You can take the determinant of this a minus lambda I, and you find, guess what? The same polynomial equation here. So you still get triple root. So the spectrum looks the same. There's 3 eigenvalues right there. So it's a triple root. So its algebraic multiplicity is 3. The difference, though, between this example and the ones where it's 0, when you try to go solve for this, you no longer get 3 directions. There's only a single direction. In other words, only one eigenvector that satisfies this. So even though you have a triple root here, there's a single eigenvector available to you. So its geometric multiplicity is 1. So the algebraic multiplicity is 3. The geometric multiplicity is 1. And this is often a very interesting case for some of these matrices that we talk about. When you have cases like that, they're called defective. So defective matrices actually are fascinating. And most matrices, a lot of times you don't have this, but when you have this, there's a lot of special properties that you have to start thinking about with them. And I'll just mention them now, because there is a class here when you have degenerate eigenvalues. In other words, the algebraic multiplicity, and if the geometric multiplicity is less than the algebraic multiplicity, it's called a defective matrix. And you could imagine if you call something defective, that means there's going to be some really interesting mathematics that you have to develop to handle them. And that's exactly the case of what you have here. In fact, I want to end this lecture with a little theorem. And here's what the theorem says. An m by m matrix A is non-defective if and only if, that's the fi with 2 f's, if and only if it has an eigenvalue decomposition A is equal to. So that's your theorem. Or another way to say it, if I can't pull this out, then I have a defective matrix. So in other words, non-defective matrices is what we're actually trying to work with. And if I have a non-defective matrix, then what I can do is I can, in fact, do this decomposition. So remember, we started this by saying, the SVD always can be decomposed, no matter what. No matter what kind of matrix A you have, you can always find a decomposition for it. Partly that's because you're using 2 different bases. With the eigen decomposition, you're committed to a single basis. And the problem with the single basis is when you have a defective matrix. If you have a defective matrix, you actually can't provide an eigen decomposition of this form. Okay, so it's important that you understand that, and it's related right here to these degeneracies. In other words, algebraic multiplicity is greater than 1. As long as everything is simple, if all the eigenvalues are simple, you get a bunch of eigenvectors, you can always do this. As soon as you have a degeneracy or a near degeneracy, remember, we're talking about computations now, right? So if 2 eigenvalues are really close together, you can have problems producing an eigen decomposition. All right, and more of that later. We're going to spend 2 more lectures talking about algorithms for computing this and also the kind of things that can go wrong. So I'm going to stop it right there and take questions.